Okay, so modelling percentage change is part of the curriculum in grade 9 and 10 for sure, but we're going to try and use it to help us analyse this change in the number of cases of COVID-19 in particular. But it is a transferable skill. So first question, number increases from 51 to 70, calculate the multiplier. So I mean, longhand it's, 51 times by some multiplier gives us 70. So clearly the multiplier is just 70 divided by 51. Okay, and when we do that on just a regular calculator, you don't need a TI Inspire, just need any old calculator will do. You do 70 divided by 51, you get approximately 1.37 to 2 dp. Now what does that mean actually, 1.37? Well, you've got 1.37 of 51 to get you to 70, so that's 137%. So this means 51 times by 137% gives you 70. So that means there's an increase of 37%, because 100% is all of the original amount. So that's how multiplier works. You guys have done this before, and so we're going to try and use that idea of the multiplier in the next few questions as well. Okay, so part 2, calculate the multiplier for days 1, 2 and 3. So we're literally, if I just zoom in on here a little bit, we saw that from 51 to 70, that was times 1. Go back, what was it again? 1.37, yeah. Okay, so that was 1.37. So we want to know what the multipliers to take us from day 1 to day 2 and from day 2 to day 3. Okay, so 70 times by another multiplier gives us 99. So this second multiplier is 99 divided by 70. And we could have 99 times by m to give us to 135. And that multiplier would be 135 over 99. Now you could be fancy, I suppose, and distinguish between the multipliers. So 70 is day 1, so the multiplier from day 1 to day 2 could be m of 2, and this could be m of 3 if you wanted. And so that means that the multiplier for the second day, I've got it here on my laptop, I've just done it in this quick calculation, that's to 2 decimal places, 1.41, and the multiplier from day 2 to day 3, we'll call that M3, that's 1.36. Okay, so I've rounded those to 2 decimal places, and then we want to know the average multiplier. So we've got a 1.37 plus a 1.41 plus a 1.36. We divide it by 3 to find the average, and we'll again round the final answer off to 2 decimal places. I've got it here, and that's 1.38. Now you might be thinking, well, is that accurate enough? What if I actually took the full value of 99 over 70 and the full value of 135 over 99, and I didn't round it to 2 dp? What if I use the full accurate answer? And the same with the 1.37. And if I didn't round all of those and I found the average, well, you'll find that if you use the full accurate answers and you rounded the final answer to 2 dp, it will still be 1.38. So we've not lost any accuracy by rounding there before the final. But it's always good to think about it. Okay, so 1.38 is the multiplier. Okay, so create a model now. C equals 51 times by 1.38 to D. And now you've got to think, well, those numbers look quite familiar. That 51, I've seen that one before, for sure. And what about over here? I've seen that 1.38 before. Okay, so we're going to unpack what this model is and how it works. Okay, first of all, we're not going to think too deeply. We're just going to go and do what the question asks us. It says calculate C when D equals 0, 1 and 2. We also want to know when it's 3 as well. Okay, so let's try it. C equals 51 into 1.38 to the 0. Well, that's 51 times by 1, because anything to the power of 0 is 1, so that's 51. Okay, C equals 51 times 1.38 to the 1. Okay, and that will give us an answer. C equals 51 times 1.38 to the 2, when D is 2. And C equals 51 times 1.38 to the 3. Okay, so let's just get those answers down here. I think I've got some answers on my laptop here. So let's have a look at those. So I've got 51, which is my first answer. And I've got 70 here, just check those on your calculator as well. I've got 97, I've just rounded those to the nearest whole number because these are the number of cases. And after 3 it's 134. Now if you look at those answers and think about those numbers, you'll see something that's quite interesting, because this 51 is the number of cases after 0 days. Now if you just go back and look at the table of values we had, that is exactly what we had in our table of values. Of course it was, look. This is 0 days, there's 51 cases, okay? So our model is telling us after 0 days there's 51 cases, and there actually was 51 cases. Okay, now what else have we got here? So the 51 clearly is the number of cases at the start of our time period. So our time period is 0 days, and that must have been the existing cases when we started timing the number of cases basically. And when d equals 1, that's 1 day after we started recording the number of cases. And with our model, we have an answer here of 70 cases. With our model for 2 days, we've got 97 cases, and for our model for 3 days, we've got 134. Okay, and you kind of quite correctly spotted that this 1.38 in here, this is actually the multiplier. So as we move from one day to the next, we're increasing by another 38%. So what we've done is we've taken our real life data in this table here. We've understood that the percentage increase isn't exactly the same. So we've taken the average percentage increase, we've taken the average multiplier of 1.38, and we've kind of smoothed out the changes a little bit, but we've got these particular values as predictors. Okay, so that's how to use the model to make predictions about what might happen, how many cases there are after 0, 1, 2 and 3 days. And then this final part, question 4, can you see I've transferred the 51, 70, 97 and 134. These are the number of cases using our model. So these are the answers for the previous question, 51, 70, 97 and 134. And we actually want to compare how accurate is our model then at making predictions, because the actual cases are here. So if you think about it, it seems to be a pretty good prediction, doesn't it? If I just take a little red colour here, the difference in cases is 0 here. The model says 51, the actual number was 51. After 1 year, there was 0 difference from the model to the actual value. Here, the model is just 2 less than the actual, and here the model is just 1 less than the actual. So the model's making really accurate predictions, okay? But we can actually quantify those differences even more. We can kind of think about them as a percentage error. Now you've got a little formula which is given in formula books down here, percentage error. Okay, so it looks a fancy formula, but basically you just want to know how far apart are the approximate and the actual, and then have that difference as a percentage of the actual. Okay, so let's just work that out for the two values that kind of count over here. So here the percentage error here equals the 134 minus 135 divided by the actual 135, and then we take that number. It might be a negative, so we'll just make it positive. We're not too bothered if we're under predicting or over predicting, and then we times it by 100. And then we do the same with the other one. Percentage error is the 97 minus 99 over 99. Take the absolute value, and then we times by 100. I'm just going to get that out of my calculator now. I'm going to do that as quickly as I can. So that's essentially 1 divided by 135 times 100. And that's less than 1% error. This is approximately 0.74%. That's less than 1% error using our model to predict how many cases there are after 2 days. That's 3 days. And the percentage error here is going to be something pretty small as well. That's going to be 2 divided by 99 times by 100. And that gives me, well, yeah, that makes sense that it's approximately 2.02%. So you can see that we've used the real data to create a mathematical model. The mathematical model is actually called an exponential model, and the exponential model relies on percentage change. It relies on the multiplier. So there you go. And then the final part here. The model is pretty accurate, isn't it, in making good predictions for 0, 1, 2, 3 days. But the final part, B, just asks us for something to go a little bit further. So when D equals 13, if we can assume that the cases increase by an average of 38% per day, so that's the multiplier is 1.38 on average over the 13 days, and that's a big assumption, because you guys know that things change quite rapidly. From day to day things change very rapidly. But we can use the model to make a prediction. We don't know how accurate the prediction is until we actually get some real data to compare it to. But we would just do 51 into 1.38 to the 13. And I'll just type that into my calculator, 51 times 1.38 to the 13. So I've got a value of 3,357 cases. Okay, so that's on day 13. So that's only 13 days after we started recording at day 0. And on day 0 we had 51 cases. So if we do 3,357 divided by 51, that's approximately, my calculator, divided by 51. Yeah, that's approximately 66 times as many cases. So that's a pretty scary thought, and that's what exponential growth does for you. If you're increasing by a percentage amount each day rather than a linear amount each day, you are going to get very big numbers very quickly. So 66 times as many cases in only 13 days, from day 0 to day 13. Okay, so I'm going to be using a lot of those ideas in the following project.